So we're going to do some example calculations of calculating the mean of a discrete random variable. We call it mu. The way you compute mu is we sum x times p of x. Here are the x's, here are the p of x's, so we just multiply this and add them up. So x times p of x, 0 times 1/8, 1 times 3/8, 2 times 3/8, 3 times 1/8. And we just sum them, so 0, 3/8, 6/8, 3/8 to get 12/8, which is 1.5. We notice here mu doesn't need to be a possible value. Since it's an average of lots of values, in many cases doesn't line up with a particular value. So here you only get the answers you get for x are 0, 1, 2, and 3, but the mean, the average, is 1.5. So somehow they're equally likely to be above and below 1.5. So when you add up all the values you can get in their relative frequency terms, you get 1.5 as an average, not one of the values. The same thing happens here with coin tossing. 1 for heads, 0 for tails. You get a probability half a half. And then if you compute the expected value, we call it that, or the mean, you sum x p of x, so x times p of x, 1 times a half, 0 times a half, that's a half, that's a half. So that's to say, if you tossed a coin many times and you wrote down a 1 when you got heads and 0 when you got tails, and then you added those up and divided by the total, you should get something like a half. Sure, because it's 1/2 heads, so 1/2 ones, the other half are zeros, don't contribute. So this notion of mean or expected value matches your experimental sense of what would happen if you did the experiment many times and added up the values and divided by n. And we could do the same kind of strategy for standard deviation. So what we want is a formula for what you would get if you were to compute standard deviations from a huge number of values. It turns out this is the formula. It has a squaring of the distance from the mean. Of course, that's not x bar anymore. And then instead of just summing over all possible values, we have each kind of value times p of x showing up. So we'll see how that might arise if you thought about doing the experiment many times and then computing standard deviation the old-fashioned way. So here again, we can imagine n observation where n very large. We compute s, square root 1 over n minus 1, sum x minus x bar. And we're thinking when n is very large, x bar should be basically mu. So that's what happens when you average more and more values from an experiment. X bar gets close to mu. That's actually called the law of large numbers, but we haven't gotten there yet. And then what we're imagining is adding up a bunch of these x minus mu's. Well, a bunch of them look the same because you only have a few possible values. So you've got xi minus mu squared happening for all the possible xi's that show up in the list. The number of xi's is n times p of xi. We said that before when we looked at the mean. Okay, so if we are allowed to do that, here's n times p of xi. We can factor this in out of the sum, and then n over n minus 1 is just about 1. So we can cancel those two. And then that gives the formula, because it's just sum xi minus mu squared times p of xi. And we don't write the subscripts here, just because it's just too cluttered for us. But that's exactly what you're doing. So this sum is over, we don't write it, right? We write it over the possible x values. Well, the rest of them have probability 0, so they won't. Even if you stuck them in, you wouldn't see it in the formula. So now we have a formula for the mean and a formula for the standard deviation. I imagine, I'm looking here, we're going to compute a standard deviation a couple times, and then we will move on. Here we go.